This video is part of a series of video instructions on the BioGrace greenhouse gas calculation tool. This is instruction 2.15, greenhouse gas emissions from boilers and CHPs. This instruction gives explanations on how greenhouse gas emissions from boilers and CHPs, combined heat and power plants, are calculated. This instruction consists of three parts. First, in the next two slides, I will give a short explanation on exergy and on allocation by energy and by exergy. Then, in the second part, I will explain how greenhouse gas calculations are made in case exergy allocation is used to divide greenhouse gas emissions between heat and electricity. Currently, the exergy allocation only applies in the BioGrace 2 greenhouse gas calculation tool for electricity, heat and cooling. However, we expect that in the future, after update of RED and X5, it will also apply for BioGrace 1 for biofuels. Finally, in the third part of this video instruction, I will explain that currently the two BioGrace Excel tools contain three different boiler CHP boxes. This is the current situation. This video is recorded in March 2015. I will also explain how I expect the situation to be in the future, after the update of RED and X5. Let me start with two introductory slides on exergy allocation. Exergy is a thermodynamic concept that describes the maximum useful work that can be done by the available energy. Exergy considers different values of heat and electricity. The exergy value of electricity is higher than the exergy value of heat, and the exergy value of heat at high temperature is higher than the exergy value of heat at low temperature. You can find some more explanations on exergy in Calculation Rule 4.2 and in Chapter 2 of the BioGrace 2 methodological background document. Now there are two more things to be mentioned before showing the tool. This is a figure from Chapter 4.2 of the calculation rules. This figure explains that two kinds of allocations can be made. The first kind of allocation is shown by the light blue arrows and text. This is allocation by energy in case of allocation between main product and co-product, other than heat and electricity. The second kind of allocation is shown by the orange text and arrows, which is allocation by exergy between heat and electricity. Exergy allocation can also be done between flows of heat at different temperatures. In the BioGrace 2 production pathways, there is always a boiler or CHP for the final conversion of the energy carrier into heat and/or electricity. And there can be a boiler or CHP to provide heat and/or electricity to a process producing the energy carrier, such as a pellet mill. The exergy allocation for the final conversion step here is rather straightforward. This part of the BioGrace 2 Excel tool will not be shown in this video instruction. The exergy allocation for the boiler or CHP providing heat and/or electricity to the process is somewhat more difficult, as different fuels can be used in this boiler or CHP. These boilers and CHPs are the subject of this video instruction. So let's move to the tool for part 2 of this video instruction. I will show the pathway pellets from bagasse, as this is one of the pathways in which the boiler CHP box has been included. Not all pathways include the same boiler CHP box, as I will explain near the end of this video instruction. In this part 2, I will explain how this boiler CHP box with exergy allocation works. Here you see the pellet mill in which the bagasse pellets are produced from bagasse. Heat and electricity to the pellet mill are provided by a CHP, which, as it is now, runs on bagasse pellets. In these lines there is the possibility for electricity input from the grid, and some diesel use including CH4 and N2O emissions from the use of diesel in machinery. This is the boiler CHP part. These emissions here, from electricity and heat from the boiler, are calculated from this lighter gray area here. The allocation within the CHP is calculated first, which gives the greenhouse gas intensity of the electricity and steam from the CHP. Only then the rest of the emissions in the pellet mill are calculated. We sometimes call this the step-by-step approach. In this way, there will never be an allocation between, for instance, surplus heat and bagasse pellets, which would be difficult to make, as then we would need to know the XRD content of bagasse pellets. At the top of the boiler CHP box, there are 3 drop-down lists. You can choose between boiler and CHP, which I will do later. You can dimension the CHP, which I'll do in a moment, and you can choose the CHP fuel. For this calculation, the CHP fuel is bagasse pellet, and here in this line there are no greenhouse gas emissions counted to the production of the bagasse pellets, as the greenhouse gas emissions are already taken into account. This is because there is a difference in gross amount of bagasse pellets produced per megajoule bagasse, shown here, and the net amount of bagasse pellets produced. The difference between these two numbers is the amount of bagasse pellets used in the CHP. Now you can choose the CHP fuel. You could fill in any type of fuel, for instance wood bark. If you do so, you will need to create 2 user-defined standard values. One for the CO2, CH4 and N2O emissions from wood bark production and transport, and one for the CH4 and N2O emissions from combustion of wood bark in the CHP. These values have to be entered in the sheet user-defined standard values, which is explained in more detail in video instruction 2.4. The CHP fuel can also be selected from this drop-down list. For example, if I choose natural gas, like this, you will see that the emissions for using 1 megajoule of natural gas are known from the list of standard values, as well as the CH4 and N2O emissions from combusting natural gas in the CHP. Now, before returning to these 2 fields, I will explain the rest of the calculations. Here, in line 88, the emissions per megajoule of CHP fuel are calculated. These have to be allocated over the heat and the electricity produced. The amounts are calculated here, based on the efficiencies that are given by the user in case of actual calculations. Now, using the formulas for the Carnot factor for heat at this temperature of 150 degrees centigrade, these 2 allocation factors for heat and electricity are calculated, allowing here in lines 98 and 99 to divide the emissions of the CHP to electricity and heat with other units. These are emissions per megajoule electricity and per megajoule of steam. Now, as the user will enter the amount of electricity and steam taken from the CHP in these 2 cells here, the emissions that go into the bagasse pellet mill are calculated here. In this case, we have a surplus electricity here. As a result, not all emissions of the natural gas provision and combustion are allocated to the electricity and heat going into the pellet mill, as some of the emissions leave with the excess electricity. I can easily show this. If I decrease the electrical efficiency, then the surplus electricity of 0.0206 will decrease, and the overall emission of this step, which is 30.5 grams of CO2 equivalent, should increase. So if I change this number to 16%, indeed the surplus electricity has decreased and the total emission has increased. If I further reduce the electrical efficiency to, for instance, 10%, then there is not enough electricity production to meet the demand. This red text is a warning that you are making an incorrect calculation. In this case, you can reduce the amount of electricity taken from the CHP to 0.0481, like this, and take 0.0108 megajoule electricity from the grid. Of course, you should then replace this name here into Grid Electricity Brazil, when the bagasse pellet mill is situated in Brazil, like this. Before starting this instruction, I did already enter the value for Grid Electricity Brazil into the list of user-defined standard values. Instead of decreasing the electricity production from the CHP, I could also have made another calculation. If I enter 0 here again and 0.0599 here, I could also have chosen satisfy both steam and electricity demand. Doing so, the calculation will automatically increase the size of the CHP, so that the heat and the electricity demand are both satisfied. Of course, this will require an additional natural gas input, causing the emissions of the CHP to increase further. This drop-down list has a third option, which is to increase the size of the CHP further. If you do so, you will notice that the emissions of the CHP of 38.2 grams of CO2 equivalent per megajoule pellets will not further increase. Like this. I can even increase the size of the CHP further. Like this. You see, it has no effect on the outcome of the calculation. This is because the greenhouse gas intensity of the heat and electricity will stay the same as all emissions from the CHP are allocated to heat and electricity, based on these efficiencies here and on this steam temperature here. The larger the CHP, the smaller the fraction of heat and electricity that are used by the pellet mill, where the emissions per megajoule steam and per megajoule electricity will stay the same. Or, in other words, the outcome of this calculation is independent of the size of the CHP. Now the last drop-down list here allows you to choose between CHP and boiler. If you choose for a boiler, then of course the electricity production should be zero, like this, and the electricity should be taken from the grid, like this. Also the electrical efficiency should be zero, like this. Now I can select the boiler. You will see that some rows that are irrelevant for a boiler will automatically disappear. This finalizes part 2 of this video instruction. Now in part 3 I will shortly explain that there are different boiler CHP boxes in the BioGrace 1 and BioGrace 2 Excel tools. In the BioGrace 1 Excel tool, no greenhouse gas emissions can be allocated to heat. This is because the methodology of the RED tells to make the allocation by energy content, and because heat does not have a lower heating value. An XRG-based allocation principle, the same as for electricity and heat from solid and gaseous biomass, might be introduced in the RED when the Annex 5 is amended in 2015 or 2016. As a result, the boiler CHP boxes in the BioGrace 1 tool are relatively simple, as is shown here for a natural gas boiler in the rapeseed to fame pathway. Many of the BioGrace 1 pathways contain such a simple natural gas boiler. Some of the BioGrace 1 pathways contain a CHP, like in the wheat to ethanol pathway here, where the excess electricity is taken into account through a credit based on the methodological rule described in RED Annex 5.C.16, which is further explained in paragraph 6.1 of the BioGrace 1 calculation rule. Also, this credit calculation might be replaced by the XRG-based allocation in the future, after RED Annex 5 is updated. If so, then all the boiler CHP boxes in the BioGrace 1 Excel tool will be replaced by the layout that I showed earlier in this video instruction. Now in the BioGrace 2 Excel tool, the situation is a bit more complex, as there are 3 types of boiler CHP boxes. 1. In the pure vegetable oil pathways, the same boiler boxes are included as in the BioGrace 1 tool. This is an example. In all pure vegetable oil pathways, they are the same. There is no XRG allocation in these pathways, as pure vegetable oils are bioliquids, for which the methodology from RED Annex 5 applies. So these boiler boxes will also be updated in the future after the update of RED Annex 5. 2. The BioGrace 2 tool contains the boiler CHP boxes that I have shown earlier in this video instruction. Currently, these are included in only 2 pathways in the BioGrace 2 Excel tool. However, this type of boiler CHP box will be more widely used in future versions of the BioGrace Excel tools. Last but not least, there are boiler CHP boxes in the wood pellet pathways, which are more extensive as compared to the one that I demonstrated. I will not show them here. These boiler CHP boxes were demonstrated in video instruction 2.12 on the use of the Calculate Efficiency sheet. There are 2 reasons why the boiler CHP boxes in the wood pellet pathways are more extensive. In the first place, the wood chips to be used in the boiler or CHP can be dried or not be dried, which has an influence on the outcome of the calculation. Secondly, we have learned that there are pellet mills that produce heat at different temperature levels, for instance heat at one temperature level to dry the incoming wood chips, and heat at a second temperature level to feed into a district heating network. The CHP boxes in the pellet mills allow for a calculation using heat at different temperature levels. Now in this video instruction I have shown you the different layouts of the boiler CHP boxes. The most important part of this instruction was the part 2, in which I explained in detail this boiler CHP configuration, which will often be used in future versions of the BioGrace Excel tools. The timing of updating the tools will depend on the timing of the update of RED and X5.